thing on this one also. Okay. So I graded your homework, and so I didn't. Yeah, I forgot. Like because I have two classes, I get confused. Like both of them have this project proposal. Like I think I read yours already. So, but yeah, I didn't read the proposal from the other. Uh, yeah, from the other class. So first thing, like seeing your homework, I see like you guys say maybe still have some problem with the machine learning card basic setup. So typically you have like training data. In that problem here, we don't care about the validation here. And for if you're going to do something like rigorous, like for example, like for work that going to submit a paper, that definitely you need to have like a separate validation data set as well. And then you have test data, right? And the validation data set, sometimes people now is also called the development data set, dev set. Um, so basically, like for example, you select a algorithm somewhere. For example, you select a neural network algorithms, like, but maybe I have like different parameters. Like for example, like I can adjust the number of layers, let's say, and I can try like 5 layers versus 4 layer and 3 layer and so on. And then like given the data sets there, so I'm going to train that, right? So I will train my based on the data set, I get the training error, right? So the training error will be something, and once I train that, so I should determine, okay, which is better from this one. So I don't want to use my training data to test my to select that which one is better because it will be biased. Um, and also I don't want to like use my test data to do that as well. So then I will, after I train it, maybe I have like a model like with like 5 layer model and then a 4 layer model and then 3 layer model. And I will test this model like with use evaluate this model with this validation set. And then and let's say if I have error, like based on this validation set, I have error like the 5 layer is at 0.01 and this is 0.02 and this is 0.03, let's say, then this 5 layer is better, then I will decide to use this 5 layer model. And then when I present it, okay, what's my best approach there? I'm going to present this one. Now, I will not present my error with this 0.01, but instead like I will evaluate again with a different data set with the test data set. And then maybe I got my actual error is 0. Or like based on my test data set, my error is like 0.015, let's say, that for the 5 layer. And then I'm going to report this value instead. So then I see like some of you guys are okay. Many of you somehow didn't do the testing. You only I forgot like only evaluate you use the training data uh to to generate an error. But what we want there is like you you have a set there, like we don't have like a free data set, but we only have a training set. We only have a training and testing, right? Test set, right? So you should train your model. In that case, just a linear regression model with your training set. Uh yeah, that's fine. I will prepare for that later on. But let me just make sure you guys get that. So you just um for the yes uh train it with this training set here, and then from this training set you can also evaluate the error, right? And that will be your training error. And then you also want to evaluate uh using your test set, then you have a test error. And typically if you change the model complexity, uh for example, you always see this like classic textbook, even though like I would say like it may not be completely correct because we are in the regime that is not over parameterized. But in the classic textbook case, it's always like when you increase the complexity of the model, this is the complexity of the model, um, you will have the training error will keep decreasing. So this is a training error. But on the other hand, like the test error will decrease. Test error will decrease. Typical test error will be larger than the training error. Will decrease, but then eventually will go back up again. But actually, it may go back down again. but classic textbook case will focus on this regime here. So and you're supposed to report both the training and test error, yeah, in the homework assignment. And I see like some of you actually like you also use the test data to train the model again, but that's not what you want. Your training should only be done like using the training data, and then like you just evaluate your training model using the test data, but you don't want to use the test data for training. Yeah. I hope this is kind of clear. I will prepare for a solution as well. So yeah, it may take me
Dr.
some.
Chen, can I just
Yes,
ask a question?
yes,
I've seen cross validation used
yes,
as like an alternative maybe
yes,
to present a result where training data is very limited.
yes.
Is that acceptable? Not like
Uh,
in this case for the
yes,
homework,
yes,
but
yes.
like,
It 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 depends. It depends whether people like. It really depends on reviewer. For
mhm.
example, if you are doing some evaluation, for example, like you have different nature of like publication, right? For example, you are just saying that like I'm trying to evaluate a bunch of like techniques, and I'm doing some kind of review and decide which one is better, then probably you can get away with that, right? Because this is a reasonably good evaluation. But on the other hand, because let's say if you are trying to kind of introduce a new method, you claim that your method is better than other one, then most likely people will the reviewer will scrutinize much more whether you are not basically cheating
Hmm.
uh, in the sense just using the kind of like training data or the validation data for testing for evaluation that may lead to some kind of bias, right?
So it
So
just depends on how you're using.
yeah, I guess I think so. Like if you're doing review, people will be like more kind of like yeah,
Okay, thank you.
because yeah, that's so okay. And so that's a little bit just about kind of I guess like the setup of machine learning, I guess in general. So another thing, because I see like you guys have like most of you have many of you has problem like still with computing, I guess the gradient of some one of the question I guess is like something a question like this, I guess I then trying to find that essentially it's like a gradient, but it's like the derivative of this guy. Like so this one of course is a scalar and this is a matrix, right? Um maybe let's start with like a really simple question first. Let's say A is a 3 by 2 uh, or maybe 2 by 3 is better. Like it's easier to draw it. Wide it's A is 2 by 3. Uh, so maybe I because there maybe white like that. Like A is 2 by 3. So what's the dimension of this guy again? What's the dimension of this one? Question for this thing here. Yes. So uh and yeah, that's like for several of you, I actually give a solution. For example, X transpose that or X transpose X, I guess that will not be correct, right? Because like this dimension is one, this is scalar, right? So and so maybe look at uh a different problem, like okay, very similar, like Y transpose AX. So if I want to again, let's say like A is still like 2 by 3. So if I want to find a derivative of this thing here, So that will correspond to uh, maybe I give some actual numbers here. Let's see if you guys can. I don't know. So yeah, it's okay. Maybe okay. Let's say so. What this is just a scalar, right? So let's expand that. So this scalar is really y I a I j x j, right? So so sum over I and j, right? And then I in this case I will be like from 2 to maybe I elaborate even more. I is like from 1 to 2 because uh A is like 2 by 3 here, and J is like 1 to 3 here. Now the this one, as we know, this is a 2 by 3, right? As you just said that. So basically it's composed of a matrix that is, maybe I just call this whole thing here as just a product P here. This would be something like partial P partial A11, partial P partial A21, partial P partial A12, partial P partial A13, partial P partial A22, something like this, right? Okay, I use I mix cap with like a capital with like capital. I mean like uppercase with lowercase. Yeah, but this is like same thing here. So so then what's that now? It's let me give get a specific and make it a question. So I just want to make sure you guys actually uh able to do this. So let's say I have y in this case is a, or what's the dimension of y? Even a severe question like y, what was dimension of y here? Yes. Actually, uh, 2 by 1 is better answer. Because typically we will consider column vectors as you see like here. Intentionally I have a transpose here, right? So but yeah, if you're able to say 1 by 2 is not too bad still. So let's say I have y is 1 2 and x is a 1 2 3. Can you find this? So now what is a partial or like, let me just, can you find this? So what is this then? This will be a 2 by 3 matrix, right? So if I have these values here. Okay, I guess you guys probably like have difficulty for this one. Maybe we step back a bit. Just just this in general, let's say y and x here. I have this y and x. in general case. So let's me cross out this question, right? So it looks like everyone is stuck. So in general, for this one here, right, I'm taking like partial derivative with respect to A11, A12, and so on and so forth. Now just focus on one term here. What will be this one? Can you tell me what is this one? So after this question is that like what is partial that's basically y transpose a y partial A11. Oh, sorry, this is x. I have a are you guys trying to compute that? Like, so wait. Uh, it should be relatively easy. So okay, so I really not don't know like so. You guys are familiar with summation like rotation like so what's this thing really if I okay maybe what's this one like things here just write down the whole. So how many terms? Okay. This is still a question. I will keep it here. But how many terms do I have here? How many terms in here? Oh, sorry, it should be there. Another in this one. Yeah. Okay, that's good. That's good. Right. So then okay, I can pull out that terms. Okay, what will be the terms? Right. I have y1 a11 x1, right? First term. Second term like y2 a21 x1, let's say. And then I have y1 a12 x2, y2 a22 x2, and y1 a, let's see, I want to make sure I'm as 1 2 2 2. Yeah, I think I'm right. And 1 3 x3 plus y1 a2 3 x3, right? 6 times here. So now it's pretty simple, right? So what was this? What's this? Now if I expand this, right, what was this? Can I go back to the earlier question? Was this one here? Yes, right? So okay, this is just like x. This one will be just x1 y1, right? Or y1 x1, right? So because I only have this term here, right? This term depend on A11, all the other terms does not depend on A11, right? If I take a partial derivative with respect to A11, I'll just get like y1 x1, right? So I'm this, so therefore like this one is y1 x1, right? So I will have this the gradient here with respect to A here will be like this one is y1 x1, right? And then like let's say what's this term here? It's A21, right? A21 only have this guy, right? So it would be like y2 x1. And for this one, A12 here will be this one, right? Y1 x2, right? And so on and so forth. I have y3 x3, y2 x2, y3 x3. Oh, sorry, y2 x3, right? So that would be the gradient, right? So, but then like if you look at that, what is this? This is actually is equal to y1, y2 multiplied by x1, x2, x3, right? Is a column vector multiplied by a row vector to get back this way. So therefore, this is actually equal to y x transpose. So, and in the homework, I have y is equal to x, so therefore, like the solution is x x transpose. Yeah. So okay, I will be lazy for the solution. I will only give the third the solution for the third problem. I guess like uh the for the other question, I don't think I forgot what's the other question now, but why? Because you guys don't have much problem for the other question, but you seems to have like more. Oh yeah, that's it's just a proof for A transpose and A. So there's many way to do that. Like so, I guess like most of you get it correct. So but you need to make it really a proof. Like I mean, like I think like some of you like make assumption that it's not in the so okay maybe I will go through that one even. Like so we have just quickly we want to show A transpose inverse is equal to inverse transpose, right? So and some of you like start with like saying that okay I assume A transpose is equal to A something like that, but you cannot, right? This is the point that you cannot introduce new condition like not existing in or assumption not existing in the original statement, right? So you want to prove this statement, you cannot arbitrarily add something that to put in. This is like so-called this strawman argument, a strawman like what's that? Like that people like to use to in a debate that being like vicious that like just put things in people's the opponent's mouth, right? Basically, he didn't say that, but he just say it for him. So in this case, the same way, math is like very rigorous. Like you you cannot just add an assumption that is not there. So then here, if I want to show that, I just say okay, A transpose. I would just use the fact that like A B transpose is B transpose A transpose. This can be easily shown as well. But let's assume we know that. Then we have what A transpose. Uh, let's see. Maybe I can call like B is equal to A transpose. Like B is A transpose. Then like B inverse or like how do I do it? It's better. A transpose times okay times that's that's the problem when you get out of the script. Sometimes you just get stuck yourself. This is a bad thing. So okay, like it should be very simple, right? So let's see. So but uh very simple, but then like when you need to start thinking, then sometimes you get stuck. Yeah. So okay, I want to show that this inverse is this guy. Okay. Maybe I don't even need this, right? So I okay, if something is like the inverse of that, I multiply by this, so it should get back the original thing, right? So let's say if 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 okay, I claim this is the inverse. I don't know. I mean, let's say like I do something like this first. So um, this is equal to a uh, a inverse a transpose, right? That's basically just from here. So then this is of course this identity. So that means what? That means that this guy is actually inverse of this guy, right? So therefore it's equal to A transpose inverse. Like that. So okay. Yeah. So um yes, so I'm not going to show the solution for I mean pin down write down the solution for the first two part, but first two questions. But I will give you guys solution for the third part. So okay, that's about the homework. And One more comment about the homework is like, for the assignment, actually, I really want you to do first principle like there. Like I guess I specified that like to do this when you at least you do the pseudo inverse thing. So you have AX, do the linear regression is equal to Y, and then like do the pseudo inverse to get back that. So you have that A here, or like I forgot like whether we call it W there. So then the W will be something like XX transpose inverse, like whatever, something like that. Like it depends on where do you kind of like arrange the data. Yeah. So something like that. So I mean like I think it's actually very important that you're able to do things from first principle, especially for stuff is like as simple as this. Um, Especially when you're new to an area, uh, it is good to try something like you're familiar with, right? Because like you know from first principle, and you know for sure like how to do matrix multiplication, right? So that's one last thing that you're going to figure out. So then if you need to debug, you're quite sure like nothing is going to get wrong. For example, I see some of you guys trying to take advantage of the API there, but you misunderstood the API. I guess a couple of you. So I forgot which function you try to look at, but that function is actually not doing the same thing as I was supposed to do. So that's the uh, that's that's the problem. That when you get into a new area, and then like there's lots of stuff that you may not know, and the documentation of packages is not always perfect. It's easy to misunderstand something like what the documentation or like what the function is supposed to do. So um so therefore like yeah, it's good to start with first principle, especially stuff is really simple. Like no, I'm not showing the code actually. I'm not showing the code here yet. Uh um but you can see like I'm kind of like sketching, right? So okay, yeah. So um yes, yeah, I would just I would show you the I would just say put the solution in Discord. I guess I share with you guys for Discord. So but yeah, that's my final remark basically. So is so yes, okay, okay. I guess I will just move on. um from what we talked about last time basically. So we ended like doing back propagation for, let's say, I guess for a oops. So we last time we ended to talk about back propagation, like just for example, like we have like, let's say, softmax layer at the end, and then also with just want to use cross entropy to compute the loss. So and let's say I have like just before the softmax, I say I use O here. Maybe I don't use, oh yeah, it's okay to use O here. Let's say just follow what I had in the notes. And let's say like here, like typical what is going on is like this is doing a classification, right? You have O here is like some kind of score, like for like a number of classes. Let's say I have C classes here. So maybe I have O, maybe C is a 3. I have like class cat, dog, and pig, let's say, right? So this have like always like a vector of um, 3 coefficients, like to have like cat score, dog score, pig score, and then like let's say the cat score is higher, so it's kind of like classified as cat, right? And we mentioned that like we can use softmax to kind of transform the scores into probabilities, right? So the softmax is doing is just like doing exponential, this OI, and some more further exponential, and then normalize that. So something like that, right? Maybe I use different index here. So that will be like my, let's say, let me use S this time. So let's say this is Si, would be like that, right? And then we compute the cross entropy. Let's say I have Q here is uh, the the probability of like, okay, let me here, like let me make it even more general. Last time we saying that we have a ground truth, let's say like I have let's say if I classify as a dog here, so then my Q also have like three values here, like the ground truth here will be the distribution uh of, or like what should I say, or like I should say will be the ground truth probability, right? So in this case will be like Q dog will be one, and then like Q cat will be zero, Q pig is equal to zero, something like that. So, but let's say I make it general, maybe like in the ground truth, like it can have some uncertainty as well. I I don't need to have this distribution like a delta function here. I can have like the Q in general is just my ground truth. Maybe I have Q cat is equal to 0.1, and then Q dog is equal to 0.8. Maybe it's have difficulty to kind of like recognize whether it's a dog or pig or like whatever. And then like maybe Q pig is 0.1 as well. Now based on this Q, the ground truth here, I can compute the loss, right? The loss will be, as I said, the cross entropy loss is log, let's say Q I for all the classes here. Maybe I use a I equal to 1 to C here. Log SI. That's the cross entropy loss, right? And that's the loss. Then if we backprop back, uh, that basically, let's say what we want to see is like what is the, or maybe like I have a simple question again. Say, what's the, let's say the number of classes is C. What is the dimension of parcel L, parcel O here? Dimension? Yes. Oh, yes. Yeah. We have three here. So in general, C plus C times one. Yes. Um. Good. So and then like, we say that like for backprop, what we're doing is I basically, for example, if I want to find this parcel L, parcel O, I can think of like parcel L, parcel O. Okay, this one is actually parcel L, parcel S. That is the intermediate output here after the softmax, and then parcel S, parcel O, right? Okay, now maybe another thing, like what's the another question, like what is the dimension of this guy here? Or maybe like, okay, number of element of this guy here. So make it a little bit more precise because a dimension maybe uh, it depends how you arrange that. Uh, how many elements do I have like in parcel S, parcel O here? Yes, some, yeah, okay, good. Yes, that yeah, you have, yeah, be very careful. Like so this should be line elements here. As I said, like you if this is scalar, then the dimension of this gradient should be like the same as your number variable here. But here this is not scalar output here. So actually the dimension of this one is in general is like, or number of elements will be the number of output multiplied by the number of input. Um and so, okay, as we said last time, like this, like okay, this chain rule is good, but this can be okay misleading because I, what do we mean by this multiplied by this? Because I, and also like the order may be like important. So the way I usually see it is I will always consider uh, I mean, instead of like this part as a scalar, I will consider as like if I want to consider the relationship of like L and O here, it can go for like S or like different coefficients of S. So therefore, I can think of this actually as a sum of like partial S1, partial S1, partial O. Okay, that's actually so already I have a summation here. So maybe I have I here, I equal to 1 to C here also like uh, and now in this case, this guy is actually a vector of dimension O, right? This is what I like. This is would be, and then this guy in this case, um, yeah, this guy in this case will be. I guess I'm not going to ask you again. This guy will be a scalar, right? So and what's partial L partial SI? Let's go back like to look at this. Maybe I need move here. So uh, partial L partial SI. So SI is here, right? SI is here. Partial L is here. Okay, L is equal to this guy here, right? So partial, therefore partial L partial SI is just equal to simply equal to minus QI over SI, right? You agree with that, right? So and partial SI partial O, that would be a vector, right? So, but let's consider the jth element of that partial SI partial OJ. That will be, I have SI here, say exponential OI over sum over exponential OK. Let's say sum over K. And then I take partial derivative OJ, right? Now I need to consider two different cases, I equal to J and I not equal to J. Uh, so let's say uh, I not equal to J first. So when I not equal to J, then this guy is like a constant, right? With respect to like OJ here. So therefore I can pull it out. So I only have like partial derivative 1 over like sum over exponential OK, right? So therefore I will have something, okay, I pull out this exponential OI and then take derivative of this with respect to OJ, then sum over exponential OK square. Oh, by the way, like why this is not a constant with respect to OJ? So everyone is following me, right? So this cannot be a constant because this contain a term. I have a summation here, but there's definitely one term that will contain OJ, right? Because this will be one of, let's say, I have O1. I'm taking partial derivative O1, O2, O3, and so on. Maybe J equal to 1. I'm taking derivative O1. Then the first term here will be like exponential O1 plus exponential O2. That okay. So therefore, I cannot treat that as a constant, right? So and then this is just a chain rule in calculus, right? I have take derivative of 1 over this. I have 1 over that's actually I need to have a minus sign here, and then take then take derivative of exponential. Okay, very simple stuff. Like what's this? What's the derivative of this guy? So it's a question here. What's the yes. Okay, so it's just exponential O. So it's I just so um, a test of your calculus. So okay, this will be exponential oj basically. So I will have this. Okay, actually that equal to this one here. But let's look at this. This is actually equal to minus exponential oi over some of this. I can just split this into two of this, right? And then I exponential oj sum over exponential ok here. But this is actually just the, oops, just here, right? Just equal to maybe I move down here. Just the output of the softmax, right? So basically, it's like just doing softmax of the, okay, maybe yeah, maybe it's okay. I don't want to copy that. So this is actually just applying softmax on the whole thing, and then the OI output, right? So therefore, like this is just equal to SI minus SI and SJ, right? So it's like, yeah. And this is like for the case when I not equal to J. So when I equal to J, then I will have take derivative OI exponential OI sum over exponential OK, K, right? So then this, now this guy will not be independent of OI as well, right? So I cannot pull it out. Then I take derivative of this first, and then okay. Anyway, so what you get like will be okay. Will be equal to um as actually let's just do it anyway. So I will have like, actually if I will first I take derivative of this guy, and then this treat as a constant, right? So I will have basically equal to exponential OI sum over exponential OK sum over K here. And then I will take derivative of this guy and treat this as constant. That will be same case as here. So actually will give us minus exponential OI square in this case. Exponential OK square. And so therefore this will be equal to minus SI square, SI minus SI square, something like. So I want to make sure let's see. Maybe I did a mistake here. Let's see. Sorry, SG. Oh, okay. It's all right. It's all right. It's right. Yeah, I just want to make sure. So all like I can write like that, 1 minus SI. Now then I can plug that into this one here, right? So I have uh partial L partial SI is here. Yeah, I'm sorry about that. Like, it's okay. I should go back to this equation here. So maybe I erase this whole thing now. Oops, wrong key. I might have this one here is actually equal to minus SISJ when I is not equal to J, and SI 1 minus SI when I equal to J, right? And so let's see. So this one then like this guy is a QI over SI, right? Sum over I equal to 1 to C here. And this one, as we said, is a vector, right? It's a vector like this. So I have basically when I is not equal to j is si um, s1, let's say. And then I have the ith term, like this is, let's say this is the ith term here. And then I si, s2, and so on and so forth. Then I up to the ith term, I have like si1 minus si instead, right? And then so forth. And then the rest is a minus si sc, let's say. Then I can have the si cancel, right? Si is all cancel here. So I will have something like sum over I equal to 1 qi uh, minus s1 s, okay, minus s2, yeah, that's fine. Let's keep the minus here. And then 1 minus si somewhere. This is the ith term. And then I minus sc, right? Okay, it looks a bit ugly, but it not too bad. But we can simplify much better. So this will be um this will be equal to, if you think of that, like you sum over this, like for I, for example, just focus on the first term here, first coefficient here, first one here. I will have like whenever I is not equal to 1, I will just sum of them together. Right? So the first one is basically equal to uh, something like 1 minus S1, because when I equal to 1, I will have this one here, right? So when my I is here, then I will actually have 1 minus S1 here. And then like for the rest, I will have like minus S2, minus F3, and so on, like blah, 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 blah. And then like for the second time, I will have S1 minus 1 minus S2 minus S, sorry, this is minus S1 minus S3, and so on and so forth, right? Um, I will wait a sec. I'm sorry, I'm missing Q here. Uh, let me rewrite that. I mean, I miss the Q here. So that would be like Q1 here, and this is a Q2 here minus Q2 S2 minus Q3 S3. Oh, sorry, there's no S2. Sorry, it's still S1 minus Q4 S1, and so on and so forth. And then second one is a minus Q1 S2 and minus Q2 1 minus S2 minus Q3 S2 minus Q4 S2, and so on and so forth. Okay. Now so you see, like I will have this is plus. Okay. I'll have like except the for these guys here, for the West is basically just like S. Okay, then maybe I just focus on one of them. Like I don't need to really go through. Let me just focus on the first coefficient. What I have is basically Q1 1 minus S1 plus sorry, minus S1 sum over Q's, actually sum over all the Q's except like I is equal to 1. So like this, right? So but like Q is probability, right? So Q is probability, therefore this is actually equal to 1 minus Q1. So therefore like this would be equal to simply like Q1 1 minus S1 minus S1 1 minus Q1. Then I will have what? Q1 S1 got cancelled, right? And I only get like Q1 minus S1. And similarly for the rest of the coefficient, therefore the entire vector will be like Q1 minus S1, Q2 minus S1, S2, Q3 minus S3, and so on and so forth. And uh, I could have a sign. Okay, yeah, I have a sign error here. So this one here, parcel L, parcel S, I actually have a negative sign here. So I put back a negative sign here, negative sign here. So I have like S minus Q is S1 minus Q1, S2 minus Q2, and so on and so forth. Okay, so sorry, like it's a little bit long, but like then we digest that. It's really nice, right? What we have is like this is the derivative of what's the derivative for that? Like it's the loss with respect to the output, right? So basically, what we have is like this is saying like how we should adjust or like okay, think of this way. So if I have like my expected or like my output softmax value is already equal to Q, then I nothing to change, right? So therefore the gradient will be equal to 0, right? And if my S, let's say my S1 is bigger than Q1, let's say, then what should I do? I will have the gradient is positive, right? So here, this for this coefficient here, or the derivative here is positive. So I should, if I want to minimize the loss, I should decrease this way. So decrease that, like meaning that I should make what O to be smaller, right? O1 to be smaller. So meaning that I should decrease the score there, right? So it actually totally makes sense, right? So I repeat again. Like, so here the remember like I have like the score here, and then I get the softmax value like transform into probability. I get this softmax here. Softmax is like transform into like some kind of probability. S is like some kind of probability, right? And that compared with the ground truth Q here is also probability. So if my probability, like for example, like for the dog cast, let's say S dog is more higher than the ground truth probability. So if I want to adjust that, I should go to the gradient descent, right? And the gradient in this case would be like equal to S dog minus Q dog, right? And that, by the way, that's the gradient for the for not for the score, but for the not oh, sorry, not for the probability, but for the score here. So I should have like I have O dog should go down, should be like O dog, or like maybe I write like this O dog. If I just use gradient descent, I should have like O dog minus times delta, right? Something like that. So okay, this is a long example, uh, but it's kind of like if you think of that, it's actually it's uh, it's very neat and elegant, and this gives you like another rationale, like at least like somehow like convince you like intuitively like softmax and with cross-entropy is actually a correct combination basically. Okay, I guess I will simply move on to okay beyond Backprop. So wait a sec. I need to pull out a. Oh, okay. Maybe I can just use here. So as I mentioned, I will talk a little bit activation function, but I'm not going to like just go through all of them, like whatever history and whatever. But here is just a quick summary slide, not slide here, but like quick summary, like one kind of picture to summarize some of this activation function here. So of course, like sigmoid has been introduced first, or like because I think of like people right at the beginning think of like new one is just active or not active, like so therefore like it's like should be like the first one, it should be just a step function, but that because it's not kind of differentiable, it's not very practical. Then eventually, actually, like very quickly, people move into sigmoid, and then like 10H is I just make it zero min. So by the way, like it's actually um, good in some sense to have your activation function, to the output of the activation function to be not just like all positive or all negative. So, but I don't. I mean, like okay. But at the same time, because you see like value apparently violate that. So, but the argument is like reasonable. So let's say if I have the activation function is all positive or all negative, I will have what? I will have let's say think of linear layer. So I have like let's say I have a linear layer, I have W, let's say it's a linear layer that I have X here that go for the linear to get Y. And then like I have the activation function somehow. Or actually I should have the activation function before that. Let's say I have the activation function here. And now, so if I go back, I backpop back. So do you still remember? Okay, what so okay, this is like just let me just make it simple. Like y is a scalar. Let's say y is a scalar, and x a vector in this case. So w is a vector as well. So I have parcel L, parcel X, parcel W. Let's say I don't want to see like how I'm going to change the weight, right? So therefore, I need to find the gradient with respect to the parameters W here, right? And that I can use chain rule that will like parcel L, parcel Y, and then parcel Y, parcel X, right? Something like that. Sorry, not X, parcel Y, parcel W. Yes. So okay, what's this one? Should be very simple. What's parcel Y, parcel W here? Yes. So this is simply X, right? So because like Y is equal to uh, WX, or like actually more precise, it should be W transpose X, right? And now if I have like an activation function here, is like the output is always positive. Like if I have a value, then my X will be always positive, right? So always positive, it means that like I have my X here for all its like coefficients, I will be can all either be okay, basically can all only be like all positive. Then like if I think of the gradient here, so because this is just X, right? This is just X. And in this case, parcel L, parcel Y is just a scalar, right? Because like Y is a scalar here. Um, then this guy will basically this gradient can only be all positive, like all the values here. So this is okay. This is a vector, right? This is a vector. It's actually just X. It can be like either all positive. Okay, or like maybe I just write. So this is just actually equal to parcel L, parcel Y, X, right? But we say that X is actually output of this activation function. That the activation function only take positive values. Then this thing, this gradient can either be all positive if this is positive, or all negative if like parcel L, parcel Y is negative, right? So then what happened is like, for example, if you just think of like a 2D case, let's say X is just a 2D, so have like only value X1 and X2. So then the gradient in this case I will have like either uh, uh, this parcel L, parcel W then will be either in this region, right? Either both x1 and x2 are positive, or in this region, like either x1 and x2 are negative, right? Now, if I think of like, for example, if I need to do uh, gradient descent along this direction here, so maybe I'm not sure. That's just a question to see like whether yeah. Can I have like gradient design like this? Oh, like this may not be apparent. I don't know. Like this is a good question or not. So or maybe I make it simpler. So let's say I start with like let's say I start with a point like here, like I start with a point here. Now I have a the gradient descent update that basically I have uh my W. My W is updated by W minus the gradient, right? Parcel L, parcel W. I start with some delta, like the learning rate here. Now, say this is like for the iteration like n, then up to like iteration n plus one, right? Like this, I say this maybe like, and also like and let's say this is like my W0 here. Can I in the next step add here W1? A question of yes or no. Can I? And yes, I can, or no, I cannot. Oh, okay. Oh, okay. Wait a sec. Like maybe the setup here is like assuming that like I have x here uh is output from a activation function that only can have positive values. So I have this activation function. For example, value that only. Yeah, the answer should be no because I if I have, as I just mentioned here, that if I have my activation function only is I only kind of like give positive values, then I only can have gradient on this. I mean, okay, my yeah, my gradient can only uh here, like in this area here, or like in this area here, right? So therefore, like if you're going to down step, I can only go in this direction or this direction, basically. So then the best you can do in gradient design in this case will be something like this. I go down here, and then maybe next step is there, and then like here, and something like that. But you cannot go say this direction like a bit faster, something like that. So this is like one argument people saying that like actually, um, if you have not zero or like if you have not activation function just like all positive or not all negative, will give you better, not better convergence, quicker convergence potentially. Even though like in practice, I guess like we're not doing quite well in many cases. Um, and another remark is like, well, I guess I maybe Velu is doing so good because if you compare with Sigma and 10H, because Sigma and 10H have their own problem as well. Like this kind of region is killing people because like whenever you fall in this region, like what does that mean? So remember that when you do backprop, like you have the activation function here, like somewhere. Let's say I have this activation function here. Right? Maybe I have the sigma here. This is the activation function. And when I do backprop back, let's say I have my input like is at this range here, is like at this range here, like at this point, like, as soon as I zero here. I have x is like at this point, I get some value y here, whatever. And when I backprop back the gradient, so I should have like, let's say parcel L, parcel X should be equal to like parcel L, parcel Y, parcel X, right? But then the problem is like at this point here, parcel Y, parcel X is almost equal to zero, right? Because at the saturated region for like 10H and also sigma, like this basically the gradient is equal to zero. So you cannot back propagate back the gradient when that, or like the gradient will be just diminish to zero when you are in the saturated region. So that's actually why like value like compared with like earlier cases is so much better. Even though like you have one range here, say not doing anything, but at least it's here like you don't have the saturation problem. So and because of that, like people also think of like, okay, how about we do this kind of like so-called leaky value. So on this side also I can put a little bit something here. So it's, yeah, I don't have like too much experience with that. Like honestly, it can be like interesting projects still, like just play with like a simple problem and test all the activation function to see like how what do you get, like basically. And also like there's some variation, like let's say how about I do some parameterize of this. For example, I have this slope here, right? I can make like two different slopes, right? For example, like even like this liquid value, you may parameterize this slope here, right? So in the original liquid value, I just fix the slope, let's say 0.1 here. But maybe I can parameterize that to be something, and this is like a parameter I'm able to train it as well. So I guess like that is like called p-loop. I'm not sure it's a good way, correct way to pronounce that. Parameterize value. And then you can also do like parameterize both ways. So then it have this like mass out thing, like parameterize like yeah, I can have like different slope in two, I mean in both dimension as well. Or you have like people who call this ELU is basically like the value, but you smooth out a little bit and also like extend kind of like uh have some non-zero element on the other. Oh, of course, it's the same also like for the liquid value here. So in both of these cases here, like it's kind of address the issue that value is only have like positive output. So, but I don't know. Like I have some simple uh when I solve some simple problem, I don't see that actually a major issue. Like uh of course maybe I didn't do like enough experiment. Like if I try many different things like that may be different. So one thing now is getting popular is Scalar. Also is like using like in bird and so on. Like I would see like if uh yeah, I would see if I would like to talk more about that. But basically, if you are just interested to try out activation function, like of course for um I'm sure for Keras as well, for Torch, right? PyTorch, right? All these activation functions already like implemented. Like you just change the name, you get a new activation function basically. Um yeah, I'm sure like for Keras and TensorFlow it will be the same also. And yeah, and I guess okay, I guess I will. I'll just for the moment I talk so much about activation function. Maybe I'll come back later on, like, but we'll see about that. So you guys have any questions for that? So so and another thing like, okay, one thing like you, I guess a a million questions, actually more than million, was like how to train a deep neural network, right? So um, I guess around '06 or '07, people like start actually even actually I should be like a little bit before that, but at least like in the publications, like people start to know like how to train deeper network, but they do it quite differently. I'm not sure I will go through that. Like in the sense like at the time like people like trying to train deeper network by doing like so-called unsupervised like pre-training. So they take a neural laterals, like for example, you have deep laterals. You take a pair of like laterals and trying to train it like in pairwise, and then after you train that, you get some initialization of the coefficient, and then afterward you start continue to train that end to end. So, but nowadays, typically you don't need this pre-training. Actually, no one do this pre-training anymore. Um, and people get much better uh, with several things. Like one thing is, for example, it's actually important is using value, I guess, because I just the saturation is in the classic iteration function, like sigma and tanh. It's very hard to train like over deep network because like you eventually get overflow or underflow somehow. Right? So if whenever you have some point, you get okay in one particular layer, you get the input is it's going to the saturation region, and basically you die, right? The network just not going to do anything. It cannot be trained anymore because I basically the information flow just stop. You try to backprop back the gradient at the point like this layer that have a activation function like or like have the input that have the activation function that get to the saturation region, then stop. Like you cannot train anymore. So that's the one reason. So people switch to value or like anything that doesn't have a saturation region that just make it okay much possible to train into a deeper network. So and also like even you use while loop, there's a possibility that you may overflow underflow because you have whatever like no matter you use a 64 bits or like now it's actually often like train with a less precision for the variables. um you can like get into overflow and underflow eventually, right? If you don't control your parameters, you may have like parameter to 10 to the or I don't know 1000 or something, then like you just lost all the precision and you uh so definitely it's actually important to make sure that like your parameter don't go like too big or too small. So and what I mean is like something like this. So if let's say if I have a 10 layer laterals here, and I will end here and then talk more about that. This is about weight initialization. So in the past, maybe like a decade or two ago, people have no idea way of weight initialization. They just randomly let's say uh, initialize the weight randomly. Let's say initialize the weight, but the point is like random initialization is okay, but how big, how should be the parameters? Like should be the variance of the parameter? Let's say if I have initialized that as a let's say a Gaussian initialization um, for the W, and then let's say if I have the parameters, I have the I know this should be not the variance, but the standard deviation is 0.01. Then as you can see, like what happened is if I go through several layers, what I'm showing here is I have 10 layers here. This is the output of the layer. So if I give an input, like initial have some input like X here, after several layers, I just have the value, just like this is showing the histogram. The the value just like all just like diminish to zero. So basically I just have no output going out. So I just basically get zero here. So of course, like, if I have like input here, output is zero, then there's no way I can fit into my desired output. Let's say Y here, right? So then maybe we want to try to increase the parameter, let's say increase the size of parameter, let's say to one. Like in this case, of course I'm using sigma here. So I would just got all saturated. So I get like the the output after the activation function is either like all one or minus one basically. So again, in this case, because it's saturated as we just argued earlier, whenever we are in the saturated region, the gradient just cannot pass back. So then again, like this, we will fail to train as well. So apparently what we want is that we want to tune the parameter or tune the weight here somehow, adjust the weight here uh, uh, in the correct magnitude such that like we will not like either the output will diminish to zero or like we'll be getting the output is too big that it will fall into the saturated region. So okay, we will talk about that like the how to do weight initialization next time. So do you guys have any question? If not, I guess I will stop the meeting now, and I will see you guys like first day then. Yeah,
Thank you.
thank you.